Hello, friend. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. Or maybe it's something else entirely. Tonight I want to ask you something gentle, something that doesn't demand an answer right away. Just let it settle quietly in your thoughts. If you could keep dividing something in half a piece of paper, a grain of sand, a moment in time, would you ever reach the end, or would you fall forever into smaller and smaller pieces of reality, endlessly descending into a universe that never stops revealing itself? It's a question that has haunted human curiosity for thousands of years. The ancient Greeks wondered if matter could be cut forever. Zeno imagined a runner who could never finish a race because each step could be divided infinitely. For centuries, we believed that smallness had no limit, that time flowed without interruption, that reality was smooth all the way down. But then, in the quiet corners of mathematics and physics, someone discovered something astonishing. Reality does have an edge. A place where the universe simply stops making sense in the way we understand it. A boundary so small, so brief, so extreme, that beneath it, the very fabric of space and time dissolves into something we can barely imagine. They call it the Planck Limit. Before we begin this quiet journey together, if you find comfort in these nighttime wanderings through science and wonder, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell not for noise, but so the next quiet night can find you again. There's no rush, just whenever it feels right. Now, let's drift. Tonight, we're traveling to the smallest edge of everything. Not to a place you can visit, not to something you can hold, but to a mathematical boundary, a whispered limit, where physics itself begins to forget how to behave. The Planck limit isn't just about tiny measurements or abstract numbers. It's about the moment when reality stops being the thing we recognize, when space becomes uncertain, when time stops flowing, when the universe reveals that beneath its calm surface something far stranger is breathing. You don't need to understand everything tonight. You don't need to solve anything. Just rest and let curiosity do the listening. Let the ideas wash over you like waves on a shore, gentle and rhythmic. Some will make sense immediately. Others will simply feel true in a way you can't quite name. Because the Planck limit is where human understanding meets its most beautiful mystery. Imagine for a moment that you're holding a ruler. Not an ordinary ruler, but one that can measure anything the width of a hair, the size of a bacterium, the diameter of an atom. You keep looking closer and closer, magnifying reality by factors of 10, 100, a million. First you see cells, then molecules, then atoms with their clouds of electrons dancing in probability. Then protons and neutrons made of quarks held together by forces we're still learning to describe. And you keep going. Smaller, deeper, further into the architecture of existence. Eventually, if you could keep shrinking your perspective, you would reach a length so incomprehensibly tiny that physicists had to invent a new way to think about it. They called it the Planck length. It measures approximately 1.6 times 10 to the negative 35th meters. That's a decimal point followed by 34 zeros and then a 1.6. It's so small that if you tried to compare it to anything in your everyday experience, the comparison itself would break down. But here's what makes it profound. The Planck length isn't just small. It's the smallest measurement that has any physical meaning at all. Below the Planck length, the universe stops behaving like a place. Space itself becomes uncertain, grainy, filled with quantum fluctuations so violent that the very concepts of distance and position lose their meaning. If you tried to measure something smaller than a Planck length, you would need so much energy concentrated in such a tiny space that you'd create a black hole. The act of observing would destroy the thing you're trying to see. It's as if the universe is saying, this far and no further. Below this line, I keep my secrets. Scientists didn't discover this limit because they built a microscope powerful enough to see it. They discovered it through pure mathematics, by asking what happens when you combine three of the most fundamental constants in physics: the speed of light, the gravitational constant, and Planck's constant, the quantum of action that governs the smallest behaviors of energy and matter. When you weave these three numbers together, something remarkable emerges. They form natural units of measurement not invented by humans, but seemingly written into the structure of reality itself. The Planck length, the Planck time, the Planck mass, the Planck temperature. Each one marks a boundary where our current understanding of physics reaches its edge and whispers, beyond here, new rules apply. And it's not just about space. Time has its limit too. The Planck time, the smallest meaningful moment, lasts approximately 5.4 times 10 to the negative 44th seconds. That's a length of time so staggeringly brief that in the time it takes light to cross the width of a proton, trillions upon trillions upon trillions of Planck time units have already passed. If you could somehow experience a single Planck time unit, you would be living in a moment so short that the entire age of the universe from the Big Bang until now would contain more Planck moments than there are atoms in all the stars you can see in the night sky. Below this timescale, the word moment loses its meaning. Time doesn't flow smoothly anymore. It becomes something else, something discontinuous, uncertain, woven from quantum threads we're only beginning to glimpse. Do you see what this means? It means that the universe you experience, the steady flow of seconds, the smooth motion of objects through space, the sense that reality is continuous and predictable, is in a way an illusion constructed from something far more chaotic underneath. It's like watching a film. From your seat, the movie seems fluid and alive. But if you look closely enough, you'd see that it's made of individual frames, flickering so quickly that your mind blends them into seamless motion. Reality at its deepest level might be like that. Not smooth, but stitched together from the smallest possible pieces of space and time, vibrating and shifting in ways we can barely measure, let alone fully understand. Some nights I think about what it would mean to truly see the world at the Planck scale. You wouldn't recognize it. The calm floor beneath your feet would reveal itself as a roiling ocean of quantum foam bubbling with tiny virtual particles popping in and out of existence. The air around you would shimmer with uncertainty. The light touching your eyes would be made of photons that, if you zoomed in far enough, were never in one place at one time, but existed in a blur of probability flickering across every possible path at once. It would be beautiful, terrifying, completely unlike anything you could call normal. And yet here's the gentlest part of this mystery. You don't need to fear this strangeness. Because the Planck limit isn't something that threatens you. It's simply the way things are hidden beneath the surface of everyday experience. The universe has always been this way, wild and uncertain at its smallest scales, but calm and predictable when you step back far enough to see the larger patterns. Think of it like the surface of the ocean. From a ship, the water looks smooth, almost glassy on a quiet day. But if you dipped your hand beneath the surface, you'd feel currents, eddies, the chaotic dance of molecules colliding. Both perspectives are true. The ocean is both smooth and turbulent, depending on how closely you look. So is reality. Some people find this unsettling, the idea that the world isn't really solid, that beneath the appearance of stability lies something so strange and uncertain. But maybe there's comfort in it too. Maybe it means that reality is far richer, far more mysterious, far more full of wonder than we ever imagined. Maybe it means that the universe still has secrets to tell us, whispered at scales we can barely touch. The Planck Limit is one of those secrets. And tonight, we're going to explore it together, not as scientists trying to solve a puzzle, but as curious minds wandering through the quietest rooms of existence, where the walls are made of mathematics and the doors open onto questions we're only beginning to ask. Where did this idea come from? Who first realized that reality might have a smallest piece, a briefest moment, a boundary beyond which the old rules no longer apply? The answer takes us back to a man who never wanted to start a revolution. A man who thought of himself as a traditionalist, a preserver of classical physics, someone who believed the universe was orderly and comprehensible. And yet, against his own intentions, he opened a door that could never be closed. His name was Max Planck, and in the year 1900, in the midst of trying to solve a problem that seemed almost trivial, he stumbled upon something that would change the way we understand existence itself. But that story, quiet, reluctant, and utterly transformative, belongs to what comes next. Max Planck did not want to be a revolutionary. In fact, if you had met him in 1900, you would have found a man deeply uncomfortable with radical ideas. He was 42 years old, a professor of theoretical physics in Berlin, respected, but not particularly famous. He wore formal suits, played the piano beautifully, and believed with quiet certainty that the laws of classical physics, the elegant equations of Newton and Maxwell, could explain nearly everything in the universe. He was, in every sense, a guardian of tradition, not a rebel, not a dreamer chasing wild possibilities, just a careful, methodical scientist trying to solve what seemed like a minor technical problem. And yet, in that single year, in the process of fixing a puzzle that almost no one else cared about, Max Planck accidentally tore open a door to a new kind of reality. He discovered something so strange, so fundamentally at odds with everything physics had believed, that even he spent years trying to explain it away, hoping someone would find a more comfortable answer. They never did. What Planck discovered became the seed of quantum mechanics, the theory that would eventually lead us to the Planck limit, to the idea that reality itself has a smallest unit, a briefest moment, a boundary beyond which the old certainties dissolve. But the path to that discovery was anything but certain. It was marked by confusion, reluctance, and a kind of intellectual honesty that forced Planck to accept a truth he didn't want to believe. The problem began with light, specifically with something called black-body radiation, the way hot objects glow. Heat a piece of metal and it glows red. Heat it more and it shifts to orange, then yellow, then white, then blue. This progression of color corresponds to the wavelengths of light the object emits. Classical physics had equations to predict this glow, equations that worked beautifully, up to a point. But there was a catastrophe hiding in those equations. literally. Physicists called it the ultraviolet catastrophe. According to classical theory, as you move toward shorter and shorter wavelengths, toward the ultraviolet end of the spectrum, and beyond the amount of energy a hot object should radiate, would increase without limit. Infinitely. Which meant that every object at any temperature should be pouring out infinite amounts of ultraviolet radiation and beyond. A campfire should blind you with X-rays. Your own warm body should flood the room with deadly radiation. Obviously, this didn't happen. Reality was far more well-behaved. But the equations, the beautiful, trusted equations of classical physics, said it should. This was more than an inconvenience. It was a sign that something fundamental was wrong with the way physicists understood energy and light. Max Planck was asked to solve this problem. Not because he was uniquely brilliant, but because he was methodical, trustworthy, someone who could be counted on to find a reasonable solution without making too much noise about it. And so he worked carefully, patiently, trying different approaches, searching for a way to make the equations match what actually happened in experiments. And then, on December 14, 1900, he presented his solution to the German Physical Society. It was elegant. It was accurate. It matched the experimental data perfectly. But it required something that made no sense at all. Planck proposed that energy was not continuous. It could not be emitted in any arbitrary amount, smooth and flowing like water. Instead, energy came in discrete packets, tiny indivisible units he called quanta. The size of each quantum depended on the frequency of the light multiplied by a constant so small it had never been noticed before. He called that constant h. Today, we call it Planck's constant. In practical terms, his equation worked like this. If you wanted to emit light of a certain color, you couldn't release just a little bit of energy. You had to release at least one quantum's worth, or 2 quanta, or 3, but never 1.5, never a smooth transition. Energy at its most fundamental level was grainy, lumpy, quantized. It was as if Planck had discovered that you couldn't pour water smoothly from a jug, but only in droplets of a fixed size. And the smaller the droplets, the stranger the world would seem. This solved the ultraviolet catastrophe beautifully. At very short wavelengths, each quantum of energy was so large that it became effectively impossible for objects to emit them at ordinary temperatures. The catastrophe vanished. The equations matched reality. But Planck himself was horrified by what he'd done. He didn't believe energy was actually quantized. He thought it was just a mathematical trick, a convenient fiction that would eventually be explained by some deeper, more classical mechanism. For years, he tried to find a way around it. He wrote letters to colleagues hoping someone would rescue physics from this uncomfortable idea. No one did, because the idea was true. Other physicists began to take Planck's quantum seriously. Albert Einstein used it to explain the photoelectric effect, the way light knocks electrons out of metal. He showed that light itself was quantized, made of particles we now call photons. Niels Bohr used it to explain the strange way electrons orbit atoms, jumping between fixed energy levels rather than spiraling smoothly inward. Each discovery made it clearer the quantum wasn't just a mathematical convenience. It was real. Reality at its smallest scale was not smooth. It was made of discrete pieces, and Max Planck, the reluctant revolutionary, had to watch as the foundation he'd accidentally cracked grew into an entirely new kind of physics, one that described a universe far stranger than anyone had imagined. But here's what makes Planck's story so quietly profound. He was brave enough to follow the truth, even when it frightened him. He could have ignored the discrepancy between his equations and the experiments. He could have dismissed his own solution as too radical, too strange, and moved on to safer problems. Many scientists do this. When the data conflicts with belief, it's easier to question the data than to rebuild your understanding of the world. Planck didn't do that. He presented his quantum hypothesis honestly, even though he didn't like it, even though it contradicted everything he'd been trained to believe, even though it made him uncomfortable. And in doing so, he gave the rest of science permission to explore the impossible. Think about what that constant, that tiny number h, actually represents. It's not just a conversion factor or a quirk of mathematics. It's a measure of the graininess of action itself. Action in physics is a combination of energy and time. Planck's constant sets the scale at which that graininess becomes noticeable. When you combine h with other fundamental constants, the speed of light which governs how information can travel, and the gravitational constant which governs how mass warps space, you can construct natural units. Planck length, the Planck time, the Planck mass. These aren't arbitrary. They emerge directly from the deep structure of physical law. And what they tell us is this: below a certain scale, the universe stops behaving like a classical machine. Space becomes uncertain. Time becomes discontinuous. The smooth fabric of reality gives way to something wilder, something quantum. Planck never lived to see the full implications of his discovery. He died in 1947 after a life marked by tragedy. He lost his first wife, his eldest son, in World War I, and his second son to the Nazi regime for involvement in a plot against Hitler. But his constant, that small number he introduced almost apologetically in 1900, became the key to unlocking the deepest mysteries of existence. It's a reminder that sometimes the most important discoveries are made by people who aren't looking for glory or revolution. They're made by people who simply refuse to lie about what the numbers are saying. People who are willing to say, "I don't understand this, but it seems to be true." And there's a lesson in that, isn't there? A kind of humility. The willingness to let reality be strange, rather than forcing it into shapes that feel comfortable. Planck's quantum was just the beginning. Over the next few decades, physicists would use it to explore atomic structure, nuclear forces, the behavior of light, the nature of uncertainty. But buried within that constant was something even more profound, a hint that reality itself had limits. That beneath a certain scale, the old questions stopped making sense. If energy comes in packets, what does that mean for space, for time? Could they be quantized too? The answer, as it turned out, was yes. But understanding how required combining Planck's quantum with Einstein's relativity, with the strange mathematics of gravity, with the realization that at the smallest possible scales, the universe becomes something else entirely. Something we still don't fully understand. But before we can explore what happens at the Planck scale, before we can understand the Planck length, the Planck time, the strange foam of quantum uncertainty, we need to ask a simpler question. What exactly is the Planck length? How small is it really, and why does it matter? The Planck length is approximately 1.616 times 10 to the negative 35th meters. Let that number settle for a moment. Not because you need to memorize it, but because it represents something almost beyond human comprehension. A decimal point followed by 34 zeros, and then the digits 1616. To call it small would be like calling the ocean damp. The Planck length isn't just tiny, it's the smallest distance that has any meaning in physics. It's the ruler the universe uses to measure itself when nothing else will do. But how small is it really? Numbers this extreme don't mean much until you put them into context, until you find a way to make them feel real, even if they can never quite be imagined. So let's try. Take a single atom of hydrogen, the simplest, smallest atom in existence. Its diameter is about 1/10 billionth of a meter. Already impossibly small. You could line up 10 billion hydrogen atoms across the width of a single meter stick, and they would fit perfectly edge to edge like beads on an invisible string. Now imagine shrinking yourself down to the size of that hydrogen atom. You're standing on its surface, looking out at the electron cloud shimmering around you, wondering what lies beneath. So you keep shrinking. You pass through the electron cloud, dive toward the nucleus, and find the proton at the center 1,000,000 times smaller than the atom itself. And you still have an almost incomprehensible distance to go before you reach the Planck length. If you were to shrink a proton, that tiny dense speck at the heart of an atom, down to the size of the observable universe, the Planck length would be about the size of an average tree on Earth. That's the ratio we're talking about. That's how much smaller the Planck length is compared to things we already think of as impossibly tiny. Or here's another way to imagine it. If a single grain of sand were magnified until it was the size of the entire observable universe, stretching billions upon billions of light years across the Planck length, would still only be about as long as an average human hair is wide. These comparisons help a little. But they also break down because the Planck length isn't just about size. It's about the limit of meaning itself. Here's what makes the Planck length so profound. It's not a technological barrier, something we'll overcome with better microscopes or more sensitive instruments. It's a fundamental boundary written into the laws of physics. Below the Planck length, the concepts of distance and position stop working the way we understand them. Why? Because at that scale, quantum mechanics and gravity, two forces that usually ignore each other, collide with full strength. And when they collide, space itself becomes chaotic. In everyday life, gravity is gentle. It holds you to the Earth, keeps planets in orbit around the sun, governs the dance of galaxies across the cosmos. But gravity is also incredibly weak compared to the other forces of nature. The electromagnetic force holding atoms together is vastly stronger. A tiny refrigerator magnet can lift a paperclip, overcoming the gravitational pull of the entire planet beneath it. Gravity only becomes significant when you're dealing with enormous masses, stars, planets, black holes. But at the Planck length, something strange happens. At that scale, even the tiniest amount of mass creates gravitational effects so intense that they warp space and time into knots. Imagine trying to measure a distance shorter than the Planck length. To do so, you would need to focus an incredible amount of energy into an incredibly tiny space energy carried by a photon or particle with a wavelength shorter than the Planck length. But concentrating that much energy into such a small region would create a gravitational field so strong that it would collapse into a black hole. A microscopic black hole, yes, but a black hole nonetheless. In other words, the act of measuring would destroy the thing you're trying to measure. The observation itself would create a region of space so warped that the concept of distance would lose all meaning. It's as if the universe has a built-in defense mechanism against being examined too closely. Push beyond the Planck length, and reality pushes back, collapsing into something impenetrable. This is not speculation. This emerges directly from combining the equations of quantum mechanics and general relativity. When you ask, what is the shortest meaningful distance? The mathematics gives you a clear answer: the Planck length. Below that, the uncertainty principle, which says you can never know both the position and momentum of a particle with perfect precision, combines with the curvature of space to create a kind of foam, a bubbling, fluctuating chaos where space and time lose their smooth, continuous nature. Physicists call this quantum foam, and while we've never observed it directly and likely never will, the theory suggests it's there, hidden beneath every point in space, vibrating and shifting at scales far too small for any instrument to detect. Some scientists believe that space at the Planck scale isn't smooth at all, but made of discrete units, tiny loops or strings or geometric structures woven together like pixels on a screen. If you could zoom in far enough, space wouldn't be a continuous fabric, but a mosaic of the smallest possible pieces, each one a Planck length across. This idea that space might be quantized just like energy is one of the central pursuits of modern theoretical physics. String theory explores it. Loop quantum gravity explores it. Both approaches try to answer the same question: what is space made of? And the answer, if there is one, lies at the Planck length. But here's where it gets even stranger. The Planck length doesn't just set a limit on how small things can be measured. It also tells us something about the universe at its largest scales. In the first fraction of a second after the Big Bang, during a period called the Planck epoch, lasting only about 10 to the negative 43rd seconds, the entire universe was smaller than the Planck length. Every point in space was so close together, so dense, so hot, that quantum effects and gravitational effects were equally strong everywhere. The universe wasn't just small, it was smaller than the concept of small has meaning. During that fleeting instant, the laws of physics, as we understand them, didn't apply. There was no distinction between space and time. No particles, no forces, no structure. Just a roiling, unified field of energy in a state we can barely describe mathematically, let alone visualize. And then, in less than a blink, faster than the briefest thought, the universe expanded. Space stretched. Time began to flow. The forces separated into the distinct phenomena we know today: gravity, electromagnetism, the strong and weak nuclear forces. Reality as we experience it emerged from that tiny, incomprehensible seed. But the Planck length remains as a kind of fossil from that moment, a reminder that the universe began as something far stranger than we can easily imagine. Now, you might wonder, if we can't measure the Planck length, if we can't observe it directly, how do we know it's real? The answer is that we derive it from things we can measure, things like the speed of light, the strength of gravity, and Planck's constant. These three numbers are woven so deeply into the fabric of reality that they show up everywhere: in the orbits of planets, in the glow of heated objects, in the bending of light around massive stars. When you combine them in just the right way, the Planck length emerges naturally, not as something we invented, but as something the universe seems to use as its own standard. It's humbling in a way. Humanity spent thousands of years creating systems of measurement: feet, meters, cubits, miles, each one tied to human experience. The length of a king's foot, the distance a person could walk in an hour. But the Planck length isn't tied to us at all. It's universal. An alien civilization on the other side of the galaxy, if they understand physics the same way we do, would derive the exact same value. It's not our ruler. It's reality's ruler. And yet, for all its significance, the Planck length is also a boundary of ignorance. It marks the edge of what our current theories can describe. Below it, we simply don't know what happens. We have guesses, beautiful mathematical structures, elegant hypotheses. But no experiments, no observations, no definitive proof. Some physicists suggest that space might be fundamentally discrete at the Planck scale, made of indivisible chunks, like a pixelated image. Others propose that space is smooth all the way down, but that our ability to measure it breaks down due to quantum uncertainty. Still others believe that space and time might not even be fundamental, that they emerge from something deeper, something more abstract, like information or entanglement. We don't know yet. And perhaps we never will, because to test these ideas, we would need to probe distances, so small, energies so high, that no conceivable technology could reach them. The universe, it seems, keeps its deepest secrets well hidden. But maybe that's okay. Maybe there's something beautiful about reaching the edge of knowledge and finding not a wall, but a horizon, a place where understanding gives way to wonder, where equations dissolve into mystery. The Planck length is that horizon, a place where the universe whispers, "This is as far as you can see with the tools you have. Beyond here, you'll need new eyes." And while we've been talking about distance, about how small the Planck length is, and what it means for the structure of space, there's another limit, just as profound, just as impossible to ignore. Time, it turns out, has a smallest unit too. Time, we are told, flows. It moves forward steadily, second by second, never pausing, never reversing. We measure it with clocks, mark it with calendars, feel it in the gradual shift, from morning to evening, from youth to age, from one breath to the next. But what if time doesn't flow at all? What if beneath the smooth surface of seconds and minutes, time is made of something else, discrete moments, indivisible instants? The smallest possible ticks of an invisible cosmic clock. The Planck time is approximately 5.39 times 10 to the negative 44th seconds. That's a decimal point, followed by 43 zeros, then 539. It is the shortest moment that has any physical meaning. Below this threshold, the concept of before and after begins to dissolve. Time, like space, reaches a boundary where the old rules stop working. And just like the Planck length, this isn't a limitation of our clocks or our technology. It's a fundamental feature of reality itself. To understand how brief the Planck time truly is, we need to stretch our imagination to its breaking point. Because this duration is so incomprehensibly short that all our usual comparisons fail almost immediately. A single second, one heartbeat, one tick of a clock contains more Planck time units than there are seconds in approximately 10 trillion times the current age of the universe. If you could somehow experience reality, one Planck time at a time, a single second would feel longer than all of cosmic history repeated trillions of times over. Let's try another approach. Light, the fastest thing in the universe, travels at exactly 299,792,458 meters per second. Nothing with mass can move faster. Information itself cannot propagate through space any quicker than this cosmic speed limit. In 1 Planck time, light travels exactly 1 Planck length. That's how these two quantities are related, they're perfectly matched. In the briefest possible moment, light crosses the smallest possible distance. It's elegant, almost poetic. The universe's two fundamental limits of space and time fit together like two pieces of the same puzzle. But what does this actually mean for the nature of time? Most of us imagine time as continuous, like a river flowing smoothly from past to future. You can divide a second into milliseconds, microseconds, nanoseconds, and keep dividing forever. There's no smallest unit, no fundamental frame rate to reality. But the Planck time suggests otherwise. It suggests that below a certain threshold, time might not be infinitely divisible. It might come in discrete chunks, quantum moments, if you will, that cannot be subdivided further. Reality might not be a smooth film, but a series of snapshots changing so rapidly that we perceive them as continuous motion. This idea has profound implications. If time is truly quantized at the Planck scale, then the universe might operate more like a computer simulation than a flowing river. Each Planck moment would be a single frame, a single state of reality, followed by the next frame, then the next. The smooth passage of time we experience would be an illusion created by the incredible speed at which these frames change. Some physicists find this idea troubling. Others find it liberating. Because if time is discrete, it means the universe isn't infinite in its divisibility. There's a bottom to the well of moments, a smallest tick of existence. But whether time is truly quantized or merely appears that way, due to quantum uncertainty, remains one of the great unsolved questions in physics. The mathematics points toward quantization, but we have no experimental way to test it. The Planck time is too brief, the scales too small, the energies required too vast. Still, the concept gives us a framework for thinking about the earliest moments of the universe. During the first Planck time after the Big Bang, a period so short it defies comprehension, the universe existed in a state physicists call the Planck epoch. At that moment, all four fundamental forces were unified into a single force. Space and time were so tightly woven together that they couldn't be distinguished. The universe was hot, dense, and governed by laws we don't yet fully understand. Then, after 1 Planck time had passed, something changed. The forces began to separate. Gravity split off, first becoming distinct from the other three. Space began to expand. Time began to flow in the way we recognize it today. Everything that came after the formation of particles, atoms, stars, galaxies, planets, life, consciousness, you sitting here now, all of it emerged from that single, impossibly brief instant. The Planck time was the first tick of the cosmic clock, the moment when existence as we know it began. But here's where things get strange. During that first Planck time, causality itself might not have existed yet. Cause and effect require a sequence of events, one thing happening, then another. But if time itself was just beginning, if the distinction between before and after was still forming, then the usual logic of causality breaks down. Some physicists suggest that the Big Bang didn't have a cause in the traditional sense. It was simply the first moment. Not the result of something earlier, but the beginning of earliness itself. Before the Planck epoch, there was no before. Time in that sense didn't go back infinitely. It started. This is difficult to wrap your mind around, I know. We're used to thinking that everything has a cause, that every event is preceded by another event. But the Planck time suggests that this chain of causation has a first link, and that first link is not the result of anything prior, it simply is. Or perhaps, as some theories propose, time is cyclical. The universe might expand, collapse, and bounce back in an endless series of big bangs and big crunches, each one separated by a Planck time. In this view, the question, what came before, becomes meaningless because there is no ultimate beginning, just an eternal cycle of creation and destruction, each iteration lasting trillions of years before resetting. We don't know which picture is correct. Both are consistent with the mathematics, but neither can be tested with our current technology. The Planck time marks the edge of our knowledge, the point where physics becomes philosophy, where equations give way to wonder. But let's return to something more tangible. If the Planck time is the shortest meaningful moment, what does that mean for the nature of motion? Consider Zeno's paradox, that ancient puzzle that has troubled philosophers for millennia. Zeno argued that motion is impossible, because to travel from one point to another, you must first travel halfway. But before you can travel halfway, you must travel a quarter of the way, and before that, an eighth, and so on infinitely. Since you must complete an infinite number of steps, Zeno claimed you can never actually move. Of course, we know motion is possible, we see it every day. But Zeno's paradox points to a deep question: can space and time be divided infinitely? The Planck time gives us an answer: no. There is a smallest step. At the Planck scale, the infinite regress stops. You don't need to complete an infinite number of steps, because there is a finite number of Planck moments between any 2 points in time. Motion is possible because time is not infinitely divisible. In this sense, the Planck time rescues us from Zeno's paradox. It provides a foundation, a smallest unit, that prevents the endless subdivision that makes motion seem impossible. But this solution comes with its own mysteries. If time progresses in discrete jumps, then at each Planck moment, the entire universe updates all at once. Every particle, every field, every quantum of energy shifts to its next state simultaneously. Reality doesn't flow, it flickers faster than anything we could ever perceive. And if that's true, then every now you experience is actually a vast collection of Planck moments strung together so quickly that they blur into the sensation of continuous time. You're not living in a single frozen instant. You're living in a stream of instants, each one discrete but passing so rapidly that the gaps between them are invisible. Some researchers have tried to imagine what it would be like if the Planck time were longer, if the universe's frame rate were slower. If each moment lasted, say, 1,000th of a second instead of 10 to the negative 44th seconds, reality would look like a flickering slideshow. Motion would be choppy. Cause and effect would feel disjointed. The smooth experience of time would shatter into something alien and disorienting. But in our universe, the Planck time is so unimaginably brief that the universe can update its state trillions upon trillions of times per second without us noticing. The flickering is there in theory, but it happens so fast that we perceive only smoothness. This raises another question: could we ever detect the Planck time directly? Could we build a clock precise enough to measure individual Planck moments? The answer almost certainly is no. To measure a Planck time interval, you would need a clock that could tick at least once per Planck time. But such a clock would require energy densities so high that it would collapse into a black hole long before it could complete a single tick. The universe, it seems, prohibits the construction of any device capable of resolving its own fundamental timescale. It's another example of that strange self-protection we keep encountering. The universe allows us to calculate the Planck time mathematically, to understand it theoretically, but it prevents us from experiencing it directly. The boundary remains forever out of reach. Yet the Planck time is not just an abstract curiosity. It has practical implications for how we think about quantum mechanics, cosmology, and the nature of reality. In quantum mechanics, the Heisenberg uncertainty principle states that you cannot know both the position and momentum of a particle with perfect precision. The more precisely you measure one, the less precisely you can know the other. This principle is usually stated in terms of position and momentum, but it also applies to energy and time. There is a minimum uncertainty in how precisely you can measure when an event occurs, and that uncertainty is closely related to the Planck time. Below that threshold, the very concept of when something happens becomes fuzzy. Events don't occur at precise instants, but in smeared-out clouds of probability. This isn't a flaw in our measuring tools. It's a feature of reality itself. Time at its deepest level is uncertain. Moments blend into one another. The sharp edges we imagine between past, present, and future soften into something more fluid, more probabilistic. And this uncertainty is what allows quantum events to happen at all. Particles can tunnel through barriers, appear and disappear, shift states, because time itself gives them room to fluctuate. If time were perfectly rigid and deterministic, quantum mechanics wouldn't work. The Planck time, by introducing a fundamental limit, also introduces the possibility of quantum behavior. In this way, the briefest moment in the universe is also the source of its deepest strangeness. There's a kind of poetry in that, don't you think? The smallest unit of time, the foundation upon which all moments are built, is also the place where certainty dissolves, where the future remains open, where possibility lives. The Planck time reminds us that the universe is not a machine ticking along predictable rails. It's something wilder, more alive, more open to surprise. Every Planck moment is a branching point, a tiny instant where the quantum dice are rolled, and reality chooses which path to follow. And yet, despite all this uncertainty, the universe somehow produces order. Stars form, galaxies spiral, life emerges, consciousness arises, all from a foundation of discrete, uncertain, impossibly brief moments, stacked one atop another, faster than thought, faster than light, faster than anything we can imagine. But if the Planck time marks the shortest meaningful moment, and the Planck length marks the smallest meaningful distance, then there must also be limits to other quantities: energy, mass, temperature. And it turns out there are. The universe has a maximum temperature, a point beyond which heat itself loses meaning. The Planck temperature is approximately 1.417 times 10 to the 32nd power Kelvin. To write that number out fully, you would need a 1 followed by 32 zeros. It is the hottest temperature that has any physical meaning, a threshold so extreme that if anything in the universe reached it, the laws of physics, as we understand them, would cease to function. At the Planck temperature, matter doesn't just melt or vaporize or ionize. It transcends the very categories we use to describe it. Particles, forces, space itself, all of it collapses into a state of such intense energy that the distinctions between things dissolve. There are no atoms, no nuclei, no quarks, just pure, undifferentiated energy in its most primal form. And here's the strangest part. Nothing in the universe today even comes close to this temperature. Not the core of the hottest star. Not the explosion of a supernova. Not even the heart of a black hole as it consumes matter and crushes it into oblivion. The only place the Planck temperature is believed to have existed was during the very first instant of the Big Bang, in that single Planck time we spoke of earlier, when the universe was so young, so dense, so energetic, that everything we know today was compressed into a space smaller than the Planck length. But to understand what the Planck temperature really means, we need to talk about heat. Not as something you feel when you stand near a fire, but as a fundamental property of energy and motion at the smallest scales. Temperature in physics is a measure of how fast particles are moving. When you heat water on a stove, you're adding energy that makes the water molecules jiggle and vibrate faster. The hotter the water, the more frantic the motion. At room temperature, molecules drift lazily. At boiling point, they bounce violently, breaking free from the liquid and escaping as steam. Keep adding energy, and the temperature keeps rising. The molecules move faster and faster. Eventually, they move so quickly that they collide with enough force to strip electrons away from atoms, creating a state of matter called plasma, a glowing soup of charged particles that makes up the sun and stars. But there's no upper limit to how much energy you can add, right? You could just keep heating something forever, making it hotter and hotter with no theoretical maximum. Except, that's not quite true. At extremely high temperatures, temperatures far beyond anything we can create in a laboratory, something strange begins to happen. The energy becomes so intense that it starts to warp space and time around it. And at the Planck temperature, the warping becomes so severe that the concept of temperature itself breaks down. Here's why. To reach the Planck temperature, you would need to concentrate so much energy into such a small space that the gravitational effects would become overwhelming. Every particle would be moving so fast, carrying so much kinetic energy, that its effective mass, remember energy, and mass are equivalent, as Einstein showed us, would be enormous. And when you pack that much mass energy into a region of space, gravity takes over. The space curves inward on itself. A black hole forms. Not a massive black hole like the ones at the centers of galaxies, but a tiny one, a quantum black hole existing for only the briefest instant before evaporating in a flash of Hawking radiation. At the Planck temperature, every point in space becomes a potential black hole. The distinction between matter and gravity disappears. You can't add more energy without creating more curvature, and more curvature means the energy gets trapped, unable to propagate or interact in the ways we normally describe with the word temperature. It's a boundary built into the structure of reality. Not a technological limit, but a fundamental one. So how hot is the Planck temperature really? Let's try to put it into perspective, even though every comparison will fall absurdly short. The core of our sun burns at about 15 million Kelvin. Hot enough to fuse hydrogen into helium, releasing the light and heat that makes life on Earth possible. That's already incomprehensibly hot. If you could somehow place a single grain of sand at that temperature here on Earth, it would emit enough radiation to kill everything within hundreds of miles. But the Planck temperature is about 100 million trillion times hotter than the sun's core. The numbers become meaningless at that scale. Comparisons break down. Words fail. Let's try this instead. During the first microseconds after the Big Bang, The universe cooled rapidly as it expanded. Within the first picosecond, 1/1,000,000th of a second, the temperature had already dropped from the Planck temperature down to a mere trillion Kelvin. By the time 1 full second had passed, the temperature had fallen to about 10 billion Kelvin, cool enough for protons and neutrons to begin forming. Today, the average temperature of the universe is 2.7 Kelvin, just a few degrees above absolute zero, the coldest possible temperature. The universe has cooled by a factor of more than 10 to the 31st over the course of its 13.8 billion year history. That's how extreme the Planck temperature was. It represents the maximum possible heat, and it existed only in the first inconceivably brief moment of existence. Now you might be wondering, has anyone ever tried to recreate the Planck temperature? Have scientists attempted to reach it in a laboratory? The short answer is no. Not even remotely close. The Large Hadron Collider, the most powerful particle accelerator ever built, can smash protons together at energies high enough to briefly create temperatures of about 5 trillion Kelvin hotter than the core of any star, hot enough to melt protons and neutrons into their constituent quarks and gluons, forming a state of matter called quark-gluon plasma. This is the same state of matter that filled the universe a few microseconds after the Big Bang. It's a roiling, chaotic soup where quarks and gluons move freely unbound by the strong nuclear force that normally confines them inside protons and neutrons. For a fleeting instant, measured in yoctoseconds 10 to the -24th seconds, the LHC recreates a tiny pocket of the early universe. But even this is nowhere near the Planck temperature. The quark-gluon plasma created at the LHC is still about 10 to the 19th times cooler than the Planck threshold. To reach the Planck temperature, you would need an accelerator millions of light-years across, powered by the energy output of entire galaxies. It's not just impractical, it's impossible by any conceivable engineering. And perhaps that's for the best. Because if you could somehow create a region of space at the Planck temperature, you wouldn't just be making something hot. You'd be creating a singularity, a point where the fabric of space and time tears, where the known laws of physics surrender to something deeper and stranger. Some physicists have speculated about what would happen if a single particle at Planck temperature appeared spontaneously in our universe, perhaps as a quantum fluctuation, a rare but theoretically possible event. The calculations suggest it would immediately collapse into a microscopic black hole, then evaporate almost instantly due to Hawking radiation, releasing its energy back into the surrounding space in a tiny burst of light and heat. But here's the unsettling part. We don't actually know for certain what would happen. The Planck temperature lies at the intersection of quantum mechanics and general relativity. Two theories that work beautifully on their own but clash violently when combined. We have no unified theory of quantum gravity, yet no mathematical framework that can reliably predict what occurs under such extreme conditions. The Planck temperature, like the Planck length and Planck time, marks the edge of our current understanding. Beyond it lies territory we can glimpse only through mathematics and speculation. But there's something else worth considering. The Planck temperature isn't just a maximum for ordinary matter. It also tells us something about the nature of energy itself. In our everyday experience, there's no upper limit to how much energy something can have. You can always add more. You can always go faster, hit harder, burn hotter. But the Planck temperature suggests that this is an illusion, an artifact of living in a cool, low-energy universe where quantum effects and gravitational effects remain mostly separate. At the Planck scale, energy becomes self-limiting. Add too much, and it collapses into something else, a black hole, a singularity, a region where space and time warp so severely that the concept of adding more energy no longer makes sense. It's as if the universe has a built-in thermostat, a maximum setting, beyond which heat ceases to behave like heat and becomes something entirely different. And this maximum has profound implications for how we think about the Big Bang. If the universe began at the Planck temperature, then it began at the absolute limit of physical description. There was no hotter state before it. The Planck epoch wasn't just the earliest moment we can describe, it was the earliest moment that could exist. Some cosmologists interpret this to mean that asking, what came before the Big Bang, is like asking, what's north of the North Pole? It's a question that seems to make sense grammatically, but has no physical answer. Time itself began with the Planck epoch. There is no before because before requires time and time didn't exist yet. Others disagree. They propose models where the universe undergoes cycles of expansion and contraction, each Big Bang followed, eventually by a big crunch, followed by another Big Bang. In these models, the Planck temperature is reached repeatedly at the turning points between collapse and expansion. The universe might be eternal, bouncing forever through cycles of creation and destruction, each one reaching the Planck limit before rebounding outward again. We don't know which picture is correct. Both are consistent with the mathematics we have. Both remain for now beyond the reach of observation. But here's what we do know. The Planck temperature existed once, at least. In the first unimaginably brief instant after existence began, the universe was as hot as it could possibly be. And from that maximum heat, everything cooled. Stars formed, galaxies condensed, planets coalesced, life emerged, consciousness arose. All of it was born from the cooling ashes of that first impossible fire. There's a kind of comfort in that, isn't there? The idea that even the most extreme conditions so violent they defy comprehension, can give rise to order, structure, beauty. The universe didn't stay at the Planck temperature. It couldn't. But in cooling, it created space for complexity to emerge, for atoms to form, for chemistry to happen, for stars to shine and life to wonder. The Planck temperature is not a place of destruction, even though it seems that way. It's a place of potential, a starting point, a seed from which everything else unfolds. And while we'll never experience it, directly never witness it, never touch it, we carry its legacy in every atom of our bodies. Because those atoms were forged in stars which were born from gas clouds, which condensed from the cooling plasma of the early universe, which expanded from that first searing instant at the Planck limit. We are in a very real sense cooled remnants of the hottest moment in history. But temperature isn't the only Planck limit worth exploring. There are others, strange thresholds that emerge when you push the fundamental constants to their breaking points. One of the most curious is the Planck mass, a quantity so paradoxical that it seems to contradict itself. The Planck mass is approximately 21.76 micrograms. That might sound impossibly small. A microgram is 1/1,000,000th of a gram, far too light to feel, barely enough to see with the naked eye. 22 micrograms is roughly the mass of a single flea egg, or a grain of fine sand, or a single human cell. And yet, in the strange arithmetic of the Planck scale, this tiny mass represents something extraordinary. It's the point where quantum mechanics and gravity, two forces that normally operate in completely separate realms, become equal in strength. It's the mass at which a particle would collapse into a black hole with a radius exactly 1 Planck length across. In other words, the Planck mass is the lightest possible black hole that could exist, even if only for an instant. How can something so small be a black hole? How can 22 micrograms, less than the weight of a dust mote, warp space and time severely enough to trap light and create an event horizon? The answer lies in one of the most counterintuitive ideas in physics. A black hole isn't defined by how much mass it has, but by how tightly that mass is compressed. Concentrate any amount of mass into a small enough volume, and it will become a black hole. It's not about size, it's about density, about packing energy so tightly into space that gravity becomes inescapable. For a normal object, a planet, a star, even a human body, the amount of compression required to form a black hole is absurd. To turn Earth into a black hole, you'd need to squeeze its entire mass down to the size of a marble. To turn the Sun into a black hole, you'd need to compress it into a sphere about 6 kilometers across. But for something with the Planck mass, the required compression is far more extreme. You'd need to squeeze those 22 micrograms down to a radius of 1 Planck length, that impossibly tiny distance of 10 to the negative 35th meters. At that point, the object's density would be so staggering that it would exceed anything else in the known universe. And here's what makes this so profound. Below the Planck mass, particles simply don't have enough gravitational influence to overcome the quantum uncertainty that keeps them spread out. Above the Planck mass, gravity dominates and the object collapses inward. The Planck mass sits exactly at the boundary between these two regimes. It's where the quantum and the gravitational meet on equal terms. But if the Planck mass is so small, why do physicists care about it? Why does it matter that a particle the weight of a flea egg marks a boundary between quantum mechanics and gravity? Because it tells us something fundamental about where our current theories break down. In the everyday world, quantum mechanics and gravity ignore each other. Quantum mechanics governs the behavior of atoms, electrons, photons, tiny things with negligible gravitational effects. Gravity, meanwhile, governs the motion of planets, stars, galaxies, massive objects, where quantum uncertainty is too small to notice. The two theories work beautifully in their separate domains, but they're incompatible at a deep mathematical level. They describe the universe using completely different languages. Quantum mechanics sees reality as probabilistic, uncertain, made of discrete energy levels. General relativity sees space-time as smooth, continuous, deterministic. For a century, physicists have been trying to reconcile these two frameworks to find a theory of quantum gravity that can describe what happens when both forces are strong. And the Planck mass tells us exactly where that reconciliation is needed, at the threshold where an object's quantum nature and its gravitational nature become equally important. So far, no one has succeeded in building that unified theory. String theory tries. Loop quantum gravity tries. Both offer elegant mathematical structures, but neither has made predictions we can test experimentally. The Planck scale remains tantalizingly out of reach. Now, closely related to the Planck mass is the Planck energy, the amount of kinetic or potential energy a particle would have if it were moving at speeds or existing in fields that brought it to the Planck threshold. The Planck energy is approximately 1.96 billion joules. That's a staggering amount of energy for a single particle. To put it in perspective, one Planck energy is roughly equivalent to the energy released by burning 500,000 liters of gasoline, or the energy needed to power a small city for a day. And remember, this is the energy of a single particle. One quantum of mass energy at the Planck scale carries more energy than entire industrial processes. If such a particle existed and collided with ordinary matter, it would release that energy in an instant, potentially creating a cascade of secondary particles, radiation, and exotic quantum effects we can barely predict. It would be, in a very real sense, a tiny bomb encoded into a single quantum of existence. But do particles with Planck-scale energy actually exist? The answer is maybe. In the vast expanses of space, there are rare but extremely energetic cosmic rays. Particles accelerated to near-light speeds by supernovae colliding neutron stars, or the violent environments near black holes. Some of these cosmic rays carry energies approaching, though never quite reaching, the Planck energy. The most energetic cosmic ray ever detected, nicknamed the "Oh my God" particle, discovered in 1991, was a single proton, traveling so fast it carried about 50 joules of kinetic energy. That's the energy of a baseball thrown at 100 kilometers per hour, concentrated into a single subatomic particle. It was moving at 99.99991% of the speed of light. Even that incomprehensibly fast particle was still about 40 million times less energetic than a Planck energy particle would be. Why don't we see particles at the Planck energy? Part of the answer is that accelerating a particle to that level would require conditions that simply don't exist in the current universe. You'd need energy densities comparable to the Big Bang itself. But there's another reason, one rooted in quantum mechanics. The Heisenberg uncertainty principle tells us that a particle's energy and the duration of its existence are inversely related. The more energy a particle has, the shorter its lifetime. A particle with Planck energy could only exist for 1 Planck time 10 to the negative 44th seconds before decaying or interacting with something else. In that sense, Planck energy particles aren't stable. They can't persist. They flicker into existence and vanish almost before they've begun. The universe, it seems, allows them only as transient possibilities, not as permanent features. But there's something else worth considering. If particles with Planck energy existed during the Big Bang, and theory suggests they did, they might have left traces behind. Tiny fluctuations in the cosmic microwave background, the faint glow of radiation left over from the early universe, subtle ripples in the distribution of galaxies, patterns in the polarization of light that has traveled across billions of years. Some physicists believe that by studying these traces, we might one day glimpse indirect evidence of the Planck scale. Not by creating Planck energy particles in a laboratory, but by reading the signatures they left in the structure of the universe itself. It's like trying to understand a storm that happened a billion years ago by examining the shapes of rocks that were carved by its wind and rain. You can't witness the storm directly, but you can infer its presence from what it left behind. Now here's where things get even stranger. If you combine the Planck mass with the Planck length, You get the Planck density, the density at which matter would have to be compressed to create a black hole at the Planck scale. The Planck density is approximately 5.16 times 10 to the 96th kilograms per cubic meter. That's a number so large it defies comprehension. For comparison, the density of an atomic nucleus already unimaginably dense is about 10 to the 17th kilograms per cubic meter. The Planck density is about 10 to the 79th times denser than nuclear matter. If you could somehow create a cubic centimeter of material at the Planck density, it would contain more mass than all the stars in the observable universe combined, and it would collapse into a black hole instantly. This tells us something important. The Planck scale isn't just about small sizes and brief moments. It's also about extreme concentration, about packing energy and mass into spaces so tiny that the fabric of reality itself begins to buckle and tear. And this concentration has consequences. One of the most important is Hawking radiation, a phenomenon predicted by Stephen Hawking in 1974. Hawking showed that black holes aren't entirely black. Due to quantum effects near the event horizon, they emit a faint thermal radiation. The smaller the black hole, the hotter the radiation, and the faster the black hole evaporates. A black hole with the mass of the Sun would take 10 to the 67th years to evaporate far longer than the current age of the universe. But a black hole with the Planck mass would evaporate almost instantly in about 1 Planck time. It would burst into existence and vanish in a flash of energy so brief that nothing could observe it directly. This raises a fascinating question. Could microscopic black holes be forming and evaporating all around us all the time, at scales too small and too brief to detect? Some theories suggest yes. Quantum foam, the idea that space at the Planck scale is filled with tiny fluctuations, virtual particles popping in and out of existence, might include fleeting black holes as well. They would be part of the constant churning that happens at the smallest scales invisible to us, but woven into the very texture of space-time. We have no way to test this directly. The energies required are too high, the scales too small, the lifetimes too brief. But the mathematics allows it. And if it's true, it means that reality at its deepest level is far more chaotic, far more active than the smooth, stable world we perceive. There's also a practical reason physicists care about the Planck mass and energy. It sets a natural scale for thinking about the early universe. During the Planck epoch, that first infinitesimal moment after the Big Bang, the universe was so hot and dense that particles with Planck-scale energies were common. They collided, annihilated, transformed into one another in a seething soup of pure energy. The four fundamental forces hadn't yet separated. Space and time were not yet distinct. Everything that would later become galaxies, stars, planets, and life existed as a unified field at the Planck threshold. Understanding what happened during that epoch requires a theory of quantum gravity. And until we have that theory, the Planck epoch remains a mystery, the earliest chapter of the universe's story that we cannot yet read. But we can make educated guesses. Some physicists propose that the universe began not from a singularity, a point of infinite density, but from a Planck-scale event. A quantum bounce, perhaps, where the universe collapsed to the Planck limit, then rebounded outward in the Big Bang we observe today. Others suggest that time itself might be quantized, made of discrete Planck time intervals, and that asking what happened before the Planck epoch is meaningless because before requires a continuity of time that didn't exist yet. Still others propose that the Planck scale is where space and time emerge from something more fundamental, perhaps a network of quantum information or entanglement or relationships between abstract mathematical objects. In these models, space and time are not the foundation of reality, but products of it, patterns that emerge only after the Planck threshold is crossed. We don't know which of these ideas is correct. Perhaps none of them are. Perhaps the truth is something we haven't imagined yet, something that will only become clear when we finally develop the tools, mathematical, experimental, or conceptual, to probe the Planck scale directly. But here's what we do know. The Planck mass and Planck energy represent the point where our two greatest theories, quantum mechanics and general relativity, stop being separate and start demanding to be unified. They mark the boundary of the known and the edge of the possible. And just beyond that boundary lies one of the deepest mysteries of all. What happens when you try to look below the Planck scale? What does reality become when you push past the smallest meaningful distance, the briefest meaningful moment, the highest meaningful energy? What lies beneath? It's one of humanity's oldest questions. Dig beneath the soil and you find rock. Break the rock and you find crystals. Examine the crystals and you find molecules. Split the molecules and you find atoms. Probe the atoms and you discover electrons, protons, neutrons. Look deeper still and you encounter quarks, gluons, the fundamental particles that seem to be the universe's smallest building blocks. But are they truly fundamental? Or is there something beneath them too? Another layer hidden at scales so small that our instruments cannot reach our mathematics, barely glimpse our minds, struggle to imagine. At the Planck scale, this question becomes more than philosophical. It becomes the central mystery of modern physics. Because below the Planck length, below the Planck time, the very concepts we use to describe reality, space-time particles, forces may lose their meaning entirely. What replaces them? What is the universe made of when you look closer than physics allows? The honest answer is, we don't know, but we have ideas. Beautiful, strange, mathematically elegant ideas that attempt to describe what might exist at the deepest level of reality. And some of those ideas are so radical that they require us to abandon almost everything we think we understand about the nature of existence. One of the earliest and most influential attempts to peer below the Planck scale came from string theory developed in the 1960s and 1970s by physicists trying to understand the strong nuclear force. String theory proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating loops of energy strings. These strings are incredibly small, typically imagined to be about 1 Planck length in size. They vibrate at different frequencies, and each frequency corresponds to a different particle. An electron is one pattern of vibration. A quark is another. A photon is yet another. In this view, particles aren't really things at all. They're notes played on the strings of reality harmonics resonating through the fabric of space. It's a beautiful idea, almost poetic, and it solves some deep mathematical problems that arise when you try to combine quantum mechanics and gravity. In particular, string theory naturally includes gravity as one of the vibrational modes, something that no other quantum theory had managed to do. But string theory comes with a cost. To make the mathematics work, the theory requires extra dimensions of space beyond the 3 we experience. Some versions require 6 extra dimensions. Others require 7. These dimensions are thought to be curled up so tightly again at around the Planck scale that we can't perceive them directly. They exist folded into every point in space, but they're too small to interact with anything larger than a Planck length. For decades, physicists have tried to find experimental evidence for string theory. They've looked for subtle deviations in the behavior of particles, anomalies in the cosmic microwave background signs of extra dimensions leaking energy into the dimensions we can see. So far, they've found nothing. String theory remains mathematically elegant, but experimentally unconfirmed. Some physicists believe it's the right path just beyond our current ability to test. Others argue that a theory we can't test isn't really physics at all. It's philosophy dressed in equations. But string theory isn't the only candidate for what lies beneath the Planck scale. Another approach, called loop quantum gravity, takes a fundamentally different perspective. Instead of asking what particles are made of, loop quantum gravity asks what space itself is made of. And the answer it gives is surprising. Space is not continuous. It's not a smooth fabric that can be divided infinitely. Instead, space is made of discrete units, tiny loops of geometry woven together like the links of chainmail. Each loop has a volume of approximately 1 Planck length cubed. You can't have half a loop or a quarter of a loop any more than you can have half an atom of gold. Space in this view comes in indivisible quanta, just like energy. If loop quantum gravity is correct, then zooming in on space would eventually reveal a grainy texture, a pixelated structure where the smooth continuum we perceive gives way to something fundamentally discrete. Space wouldn't be a stage on which particles perform. It would be made of something built from something more fundamental. And time, too, would be quantized. Moments wouldn't flow smoothly, but tick forward in discrete jumps, each one Planck time in duration. Reality would update itself frame by frame like a film projected at an incomprehensibly high speed. Loop quantum gravity has its own challenges. It makes predictions that are difficult to test, and it hasn't yet been reconciled with all the successful predictions of general relativity and quantum field theory. But it offers a compelling vision that space and time are not the foundation of reality, but emergent properties patterns that appear only when you step back from the Planck scale and look at the larger picture. Both string theory and loop quantum gravity are attempts to answer the same fundamental question: what is the universe made of at its deepest level? But there's a third possibility, one that's even more radical. Some physicists have begun to suspect that space and time are not fundamental at all, that they emerge from something more abstract, something that doesn't exist in space or at a moment in time. One version of this idea is called the holographic principle. It suggests that the information content of any region of space is proportional not to its volume, but to the area of its boundary. In other words, a three-dimensional region of space can be fully described by information encoded on its two-dimensional surface. It's as if the universe is a hologram, a projection from a lower dimensional reality into the three-dimensional world we perceive. Everything you see, touch, experience, all of it, might be a kind of illusion, a shadow cast by something simpler and stranger. This idea grew out of studies of black holes. Stephen Hawking and Jacob Bekenstein showed that a black hole's entropy, a measure of its information content, is proportional to the area of its event horizon, not its volume. This was unexpected. For ordinary objects, entropy scales with volume. A larger box can hold more information, than a smaller one. But for black holes, information seems to be stored on the surface, not in the interior. And if that's true for black holes, some physicists argue it might be true for the universe as a whole. In this view, the three-dimensional space we inhabit is a kind of holographic projection from a two-dimensional surface at the boundary of the universe. Space-time particles forces all of it emerges from relationships encoded on that distant boundary. It sounds like science fiction, and yet the mathematics is rigorous. Physicists have used holographic principles to solve problems in quantum field theory, to study the behavior of materials at extreme temperatures, even to explore the nature of black hole information paradoxes. The holographic principle doesn't tell us what lies below the Planck scale in a conventional sense. Instead, it suggests that the question itself might be wrong. There is no below. There's only a different way of describing the same reality, a description where space and time are not fundamental, but derived from more abstract mathematical structures. Another intriguing possibility comes from the study of quantum entanglement. Einstein famously called it spooky action at a distance. The phenomenon where two particles once connected remain correlated no matter how far apart they are. Measure one, and you instantly know something about the other, even if it's on the other side of the universe. For a long time, entanglement was seen as a quirk of quantum mechanics, something strange but not particularly fundamental. But recent research suggests that entanglement might be the glue that holds space together. Some physicists propose that space itself emerges from a network of entangled particles. Where particles are highly entangled, space exists, and distances are well defined. Where entanglement is weak or absent, space breaks down. In this picture, the geometry of space-time is not a fixed backdrop, but a dynamic structure woven from quantum correlations. If this is true, then the Planck scale might mark the point where the entanglement network becomes too sparse to support a coherent notion of distance. Below the Planck length, space wouldn't be grainy or discrete. It simply wouldn't exist in any meaningful sense. What would remain is pure quantum information. Relationships without positions, correlations without locations. It's a dizzying idea. But it's also testable, at least in principle. Physicists are looking for ways to detect subtle anomalies in the way space behaves at extremely small scales, tiny deviations from the predictions of general relativity that might hint at the underlying entanglement structure. Now here's the challenge with all of these ideas. They live at the boundary between physics and mathematics. We can write equations, construct models, make predictions. But testing those predictions requires experiments at energies and scales we cannot reach. To probe the Planck scale directly, you'd need a particle accelerator the size of the Milky Way galaxy, powered by the energy output of 1,000,000 suns. Even then, you'd only be scratching the surface. The Planck energy is so high, the Planck length so small, that no conceivable technology could ever observe it directly. So how do we know if any of these theories are correct? The answer is indirect evidence. Physicists look for subtle effects that might leak up from the Planck scale into the world we can measure. Tiny variations in the cosmic microwave background. Slight deviations in the speed of light at different frequencies. Anomalies in the way particles scatter at the highest energies we can produce. So far, the universe has been remarkably silent. Every experiment has confirmed the predictions of standard quantum field theory and general relativity. The Planck scale remains hidden, its secrets intact. But that doesn't mean we should stop looking. Because even if we can't observe the Planck scale directly, understanding it is crucial for understanding the universe as a whole. The Planck scale is where the Big Bang began. It's where black holes end. It's where the laws of physics are written in their most fundamental form. Without a theory of quantum gravity, without an understanding of what happens below the Planck limit, we're missing the first chapter and the final page of the universe's story. And there's something humbling about that, isn't there? For all our technological progress, for all our mathematical sophistication, there's still a layer of reality that remains beyond our grasp. A place where our best theories break down, where our deepest questions have no answers yet. Some people find this frustrating. They want definitive answers, clear explanations, certainties that can be tested and confirmed. But maybe there's beauty in the uncertainty too. Maybe the fact that reality still holds mysteries, mysteries that challenge our brightest minds and resist our most powerful instruments, is a reminder that the universe is richer, stranger, more wonderful than we can ever fully comprehend. The Planck scale is not a wall that stops our understanding. It's a horizon that invites us to keep searching, keep questioning, keep reaching toward truths we can barely glimpse. And one of those truths has to do with the texture of space itself. Because if space is quantized, if it's made of discrete units at the Planck scale, then reality at its deepest level might not be smooth at all. It might be something far more chaotic, far more turbulent than we ever imagined. Imagine the calmest ocean you've ever seen. Glassy smooth, reflecting the sky like a perfect mirror. From a distance, it looks utterly still, as if the water were solid, frozen in time. But dip your hand beneath the surface and you'd feel something different. Currents, eddies, the constant motion of molecules colliding, sliding past one another, creating patterns too small to see but undeniably present. Now imagine zooming in closer, down to where individual water molecules jostle and spin, down to where the smooth surface reveals itself as a chaotic dance of atoms, each one vibrating, each one interacting with its neighbors in ways that are fundamentally unpredictable. Space physicists believe is like that ocean, smooth and calm when viewed from our everyday scales. But at the Planck length, at distances of 10 to the negative 35th meters, it becomes something else entirely. They call it quantum foam. And if this idea is correct, then the fabric of reality, the stage upon which all events unfold, the background against which particles move and fields fluctuate, is not a stable, unchanging foundation. It's a seething, bubbling froth of uncertainty, where the very concepts of distance and duration become blurred, probabilistic, strange. The idea of quantum foam was first proposed by John Archibald Wheeler in the 1950s. Wheeler was one of the great visionaries of 20th century physics, a man who helped develop the theory of nuclear fission, who coined the term black hole, and who spent decades thinking deeply about the nature of space-time at its smallest scales. Wheeler imagined that if you could zoom in far enough past atoms, past particles, past the Planck length itself, you would see space and time writhing with quantum fluctuations. Virtual particles would pop into existence and vanish in fractions of a Planck time. Tiny wormholes would open and close. The smooth geometry of space-time would give way to a turbulent, foamy structure, where the usual rules of cause and effect, position, and momentum broke down entirely. He described it as a kind of storm at the quantum level, invisible to us, but fundamental to the way the universe operates. And while we can't observe quantum foam directly, it exists at scales far too small for any instrument to reach the mathematics of quantum field theory. And general relativity strongly suggests it's real. But what does it mean for space to be foamy? How can distance itself become uncertain? To understand this, we need to revisit Heisenberg's uncertainty principle, one of the cornerstones of quantum mechanics. The principle states that there are pairs of properties like position and momentum, or energy and time, that cannot both be known with perfect precision simultaneously. The more accurately you measure one, the less accurately you can know the other. This isn't a limitation of our measuring instruments. It's a fundamental feature of reality. Particles don't have definite positions and momenta. They exist in a state of quantum uncertainty, a cloud of possibilities that only collapses into something definite when a measurement is made. Now apply this same logic to space-time itself. At the Planck scale, the uncertainty principle tells us that the energy contained in a tiny region of space fluctuates wildly. And since energy and mass are equivalent, as Einstein taught us, these fluctuations in energy are also fluctuations in mass, and mass curves space-time creating gravitational effects. So at the Planck scale, space itself is constantly fluctuating. Tiny ripples of curvature appear and disappear. Virtual black holes form and evaporate in less than a Planck time. The geometry of space-time becomes probabilistic, spread out over many possible configurations at once. This is quantum foam, a state where space and time lose their classical smoothness and become subject to the wild uncertainties of quantum mechanics. If you could somehow observe quantum foam directly, what would you see? The honest answer is that we don't know, because the scales are so far beyond anything we can measure. But physicists have tried to imagine it. Some suggest it would look like a constantly shifting landscape where distances between points fluctuate unpredictably. A straight line drawn at the Planck scale wouldn't stay straight. It would wriggle and twist as space itself fluctuated beneath it. Two particles separated by a Planck length might suddenly find themselves closer together or farther apart, not because they moved, but because the space between them changed. Others propose that quantum foam might involve topology changes, moments where the very structure of space shifts, where holes open and close, where regions of space temporarily disconnect and reconnect. It would be like watching the surface of a liquid boil, except the liquid is space-time itself. And all of this would be happening constantly at every point in space at scales so small that we perceive only the average, the smoothed-out calm that emerges when you step back and look at reality from a distance. It's a strange and unsettling idea. We're used to thinking of space as a container, a fixed backdrop that never changes. But quantum foam suggests that space is dynamic, alive, in a sense constantly recreating itself at the smallest scales. And this has profound implications for what we can and cannot know about the universe. One of the most important consequences of quantum foam is that it places a fundamental limit on measurement. Not a technological limit, but a limit built into the structure of reality itself. Imagine you want to measure the position of a particle with perfect precision. To do that, you'd need to use light with an extremely short wavelength light, with enough energy to probe the tiniest distances. But as the wavelength gets shorter, the energy of each photon increases. And if you try to measure something at the Planck scale, the energy required becomes so large that it would create a gravitational disturbance strong enough to warp the very space you're trying to measure. In other words, the act of measurement itself changes the thing you're measuring in unpredictable ways. You can't zoom in far enough to see the foam without creating more foam. The universe, it seems, has a built-in protection against being observed too closely. This is why we say the Planck length is the smallest meaningful distance. It's not that smaller distances don't exist mathematically. It's that they can't be measured even in principle. Below the Planck scale, the concepts of position and distance lose their operational meaning. The same is true for time. If you tried to measure an event with precision better than 1 Planck time, the energy fluctuations required would create quantum uncertainties so large that the notion of when the event occurred would become meaningless. Time, like space, becomes fuzzy at the quantum level. And this fuzziness is not a bug. It's a feature. It's what allows the universe to be quantum at all. In classical physics, everything is deterministic. If you know the position and velocity of every particle in the universe, you can predict the future with perfect accuracy. The universe is like a giant clockwork mechanism ticking along predictable paths. But quantum foam breaks that determinism. It introduces fundamental randomness into the fabric of reality. Events at the Planck scale are not determined by prior causes in the classical sense. They emerge from the quantum uncertainty inherent in space-time itself. This is why quantum mechanics is probabilistic. It's not that we don't have enough information to predict outcomes. It's that the universe itself doesn't decide what will happen until the moment it happens. The future is genuinely open-shaped by the constant quantum fluctuations bubbling up from the Planck scale. Some physicists find this deeply unsatisfying. Einstein famously rejected it, saying that God does not play dice with the universe. He believed there must be some deeper layer of reality, some hidden variables that determine outcomes in a way we simply haven't discovered yet. But decades of experiments have confirmed that quantum uncertainty is real. There are no hidden variables. The randomness is fundamental. And quantum foam is one of the reasons why. Now here's where things get even stranger. Quantum foam doesn't just affect particles and measurements. It might also affect the speed of light. In classical physics, light travels at a constant speed through empty space, exactly 299,792,458 meters per second. This speed is the same for all observers, regardless of how fast they're moving. It's one of the fundamental constants of nature, the speed limit of the universe. But if space is foamy at the Planck scale, then light passing through space is actually passing through a turbulent, fluctuating medium. And just as light slows down slightly when it passes through glass or water, it might be slowed down or sped up by quantum foam. The effect would be incredibly tiny, far too small to measure with current technology. But some physicists have proposed experiments to look for it. They've suggested observing high-energy photons from distant gamma-ray bursts and checking whether photons of different energies arrive at slightly different times, as they would if quantum foam affected their speeds differently. So far, the results have been inconclusive. Light appears to travel at the same speed, regardless of energy, at least within the precision of our measurements. But that doesn't mean quantum foam isn't real. It might just mean the effects are even smaller than we thought, or that our theories need refinement. Another consequence of quantum foam is that it might explain why the universe is fundamentally probabilistic rather than deterministic. In a universe with smooth, continuous space-time, you might expect cause and effect to operate like clockwork. But in a universe where space-time itself is fluctuating at the Planck scale, randomness is built in from the ground up. Every quantum event, every particle decay, every photon emission, every measurement that collapses a wave function might be influenced by the foam beneath it. Not in a predictable way, but in a way that introduces genuine unpredictability into the flow of events. This is why physicists say that quantum mechanics is not just a theory about particles. It's a theory about information, about what can be known and what must remain uncertain. And the Planck scale is where that uncertainty originates. But quantum foam raises another question, one that cuts to the heart of what we mean by reality. If space and time are not fundamental, but emerge from quantum fluctuations, then what is the universe really made of? Some physicists suggest the answer is information. Not matter, not energy, but patterns of information encoded in quantum states. In this view, particles are just stable patterns of information. Fields are flows of information. Space and time are ways of organizing information so that it can interact and evolve. And quantum foam is the substrate, the raw material from which those patterns emerge. It's like the static on an old television screen, meaningless noise, until a signal comes through and organizes it into a coherent image. Others disagree. They argue that space and time are real, not emergent, and that quantum foam is simply a feature of how quantum fields behave in a gravitational context. The debate continues, and it may not be resolved until we have a complete theory of quantum gravity. But regardless of which interpretation is correct, quantum foam reminds us of something important: the universe is not what it seems. The smooth, stable reality we experience every day is built on a foundation of chaos, uncertainty, and constant transformation. And there's a strange comfort in that. Because it means the universe is not rigid, not fixed, not predetermined. It's alive with possibility shaped moment by the quantum dice that roll at the Planck scale. Every breath you take, every thought you think, every atom in your body, all of it rests on this turbulent foundation. You are, in a very real sense, a pattern of order emerging from chaos, a temporary island of stability in an ocean that never stops churning. But this churning, this foam, this fundamental uncertainty, it's not just a curiosity for physicists to puzzle over. It has consequences for the deepest questions we can ask. Questions about the beginning of the universe, the nature of time, the possibility of other realities beyond our own. And it brings us to a final question, one that ties together everything we've explored. If the Planck scale is where reality becomes uncertain, where space and time lose their meaning, where the universe itself forgets how to behave, then what does that tell us about the limits of knowledge, about the boundaries of what we can ever hope to understand? We've traveled far tonight, haven't we? From the quiet questions of Max Planck in 1900 reluctantly discovering that energy comes in discrete packets to the edges of space and time themselves. From measurements so small they make atoms look like galaxies, to temperatures so extreme they existed only in the first flash of creation. From particles that collapse into black holes, to foam bubbling beneath the surface of every point in space, we've explored the Planck limit, that strange, beautiful boundary, where the universe stops behaving like the orderly place we know and becomes something wilder, something uncertain, something that our current theories can barely describe. And now, as we drift toward the end of this journey, I want to ask you something gentle, something that doesn't need an answer right away. Just let it settle in your thoughts, like snow falling on a quiet evening. What does it mean that reality has limits? For most of human history, we believed the opposite. We thought you could always dig deeper, always divide further, always ask one more, why? The universe seemed infinite in both directions, outward toward the cosmos, inward toward the infinitesimal. There was no smallest piece, no briefest moment, no final answer. Just layers upon layers forever. But the Planck scale tells us something different. It whispers that there is a bottom, a foundation, a place where the questions we've been asking for millennia finally encounter something new. Not an answer exactly, but a transformation. Point where the old questions stop making sense. New ones must be learned. Below the Planck length, the concept of distance dissolves. Below the Planck time, the flow of moments becomes uncertain. At the Planck temperature, matter forgets what it is. At the Planck mass, gravity and quantum mechanics collide with equal force. These aren't failures of understanding. They're features of reality itself. The universe has built-in boundaries, thresholds beyond which the familiar rules no longer apply. And perhaps, just perhaps, there's something beautiful about that. Think about it for a moment. If reality could be divided infinitely, if there were no smallest piece, no fundamental unit, then understanding the universe would be an infinite task. Every answer would lead to another question. Every layer would conceal another layer forever and ever. Knowledge would be an endless descent into complexity, with no hope of ever reaching solid ground. But the Planck Limit suggests otherwise. It tells us that reality has a foundation, that there is a deepest level even if we can't observe it directly, even if our current theories can't fully describe it. The universe is not infinitely complex. It's finitely complex, built from a finite set of rules operating at a finite smallest scale. And that means understanding it truly deeply, understanding it is possible. Difficult, yes. Perhaps beyond the reach of any single generation. But possible. It's like a story with a beginning and an end. Without edges, without boundaries, there would be no structure, no meaning, no narrative arc. The limits are what give the story shape. The Planck scale is the universe's way of saying, I am not infinite, I am vast, yes, strange, yes, but I have a structure. I have rules. And if you're patient, if you're curious, if you're willing to let go of your intuitions and follow where the mathematics leads, you can understand me. There's a kind of generosity in that. Don't you think the universe could have been infinitely complex, impenetrable forever, beyond comprehension? But it's not. It has given us clues. Constants that emerge naturally from the structure of physical law. Boundaries that mark where new understanding must begin. And we've come so far in following those clues. In just over a century, we've gone from thinking atoms were indivisible to probing the structure of quarks, from treating space and time as absolute to understanding them as dynamic, curved, woven together into a single fabric. From seeing the universe as eternal and unchanging, to recognizing that it had a beginning, that it's expanding, that it emerged from a state so extreme our best theories can barely describe it. We've built instruments that can detect gravitational waves rippling across 1 billion light-years. Telescopes that can see galaxies forming when the universe was only a few 100 million years old. particle accelerators that can recreate for fleeting instants the conditions that existed microseconds after the Big Bang. We haven't reached the Planck scale yet. We may never reach it directly. But we've glimpsed its shadow in the mathematics, felt its presence in the equations, understood that it exists even if we can't touch it. And that understanding has changed us. It's shown us that the universe is both more orderly and more strange than we imagined. That beneath the chaos of everyday experience lies mathematical structure. And beneath that structure lies quantum foam uncertainty, a foundation that is itself in constant motion. It's taught us humility, because the Planck scale is a reminder that there are limits to what we can know, not because we're not clever enough, but because reality itself places boundaries on observation. Some questions might not have answers. Some truths might be forever beyond our reach. But it's also taught us hope. Because every time we thought we'd reached the edge of understanding, we found new ways forward. When Newton's laws failed to explain Mercury's orbit, Einstein gave us relativity. When classical physics couldn't explain blackbody radiation, Planck gave us quanta. When particles behaved in ways that seemed impossible, quantum mechanics emerged to describe them. The Planck limit is not a wall, it's a horizon, and horizons by their nature invite exploration. Some of the brightest minds in physics today are working to push beyond that horizon. They're developing theories of quantum gravity, searching for evidence of extra dimensions, exploring the possibility that space and time are emergent rather than fundamental. They're looking for subtle anomalies in the cosmic microwave background, tiny variations that might hint at the texture of space-time at the Planck scale. They haven't succeeded yet, but they're trying. And every failure, every dead end, every theory that doesn't quite work, each one teaches us something new about what the universe is not, which brings us closer to understanding what it is. And maybe that's the real lesson of the Planck limit. Not that we'll never understand everything, but that understanding is a process, a journey, a conversation with reality that unfolds over generations. Each generation asks questions, builds instruments, discovers new truths. And then the next generation picks up where they left off, armed with new tools, new mathematics, new ways of thinking. You and I sitting here in the quiet of the night are part of that conversation. Not as physicists, perhaps. Not as mathematicians or experimentalists. But as curious minds wondering about the nature of things, asking questions that have no easy answers, following ideas to their edges just to see what's there. That curiosity is what drove Max Planck to accept his quantum hypothesis, even though he didn't like it. It's what drove Einstein to reimagine space and time. It's what drove Hawking to peer into black holes and discover they glow. It's what drives physicists today to search for theories that can unify quantum mechanics and gravity. And it's what brought you here tonight, to listen to a story about the smallest, briefest, hottest, strangest scales of reality. So what happens now? Where does the story go from here? The truth is, I don't know. No one does. The Planck scale remains for now beyond our reach. We have beautiful theories, elegant mathematics, compelling ideas, but we don't yet have the experiments, the observations, the definitive proof that would let us say, this is what reality is made of. This is how space and time emerge. This is what lies beneath the Planck limit. Maybe we'll get there in our lifetimes. Maybe it will take centuries. Maybe the answer will come from a direction we haven't even imagined yet, some insight so unexpected that it reshapes everything we thought we knew. But here's what I do know: the journey is worth it. Not because of where it ends, but because of what we discover along the way. Each step toward understanding the Planck scale teaches us something profound about the nature of reality, the limits of knowledge, the relationship between mathematics and the physical world. And it reminds us that we live in a universe that is both comprehensible and mysterious. A universe that reveals its secrets slowly, one Planck length at a time, but reveals them nonetheless. So as you drift off tonight, as your thoughts soften and the edges of waking blur into sleep, maybe you can hold on to this: you are made of atoms that once floated in the hearts of stars. Those atoms are made of particles that emerged from the quantum foam of the early universe. And that foam, that strange bubbling chaos at the Planck scale, is the foundation upon which everything stars, planets, life, thought, consciousness is built. You are in a very real sense the universe looking at itself, a pattern of order that emerged from chaos, a moment of clarity in the quantum foam, a question asking itself what it means to exist. And the fact that you can wonder about the Planck limit, can think about scales so small they defy imagination, can follow the mathematics to places your senses will never reach, that fact is as miraculous as any discovery in physics. Because it means the universe is not just physical, it's also mathematical, beautiful, knowable in principle, even when unknowable in practice. It means that reality is structured in ways that allow consciousness to arise, to wonder, to explore. The Planck limit is not the end of wonder, it's a beginning. A doorway to questions. We're only starting to ask truths. We're only beginning to glimpse possibilities. We're only learning to imagine. And maybe that's enough. Maybe the beauty lies not in having all the answers, but in knowing that there are still questions worth asking, still mysteries worth exploring, still truths worth seeking, even if they lie forever just beyond our grasp. We've reached the edge of the smallest, the briefest, the most fundamental scales of reality. And we found that the edge is not a wall, but a window. A place where understanding gives way to wonder, where certainty dissolves into possibility, where the universe whispers, "There is more, always more. Keep looking." So rest now. Let these ideas settle like stars finding their places in the night sky. You don't need to understand everything. You don't need to solve the mysteries of quantum gravity or peer beneath the Planck length. Just know that the universe has limits, and those limits are not barriers. They're invitations. Gentle reminders that reality is deeper than it appears, stranger than we imagine, more beautiful than we could ever fully describe. The Planck limit is where physics forgets itself, but it's also where it remembers what it's for: not to conquer nature, but to listen to it. Not to dominate reality, but to understand it. And in that understanding, we find something precious. Not certainty, but meaning. Not answers, but better questions. Not the end of wonder, but its deepest source. Thank you for traveling with me tonight through the smallest corners of existence to the edges where reality becomes uncertain and the familiar rules dissolve. Thank you for your curiosity, your patience, your willingness to wonder about things that can never be seen, only imagined. The universe is vast, but it is also comprehensible. And every time we ask a question, every time we follow an idea to its edge, we become part of the long conversation between consciousness and cosmos between wondering minds and the reality they inhabit. There are more stories to tell, more mysteries to explore, more quiet journeys through the landscapes of science and wonder. And I hope you'll join me again when the night is still and your mind is ready to drift to explore the next question, the next mystery, the next beautiful truth, hiding in the equations and observations of those who came before us. Until then, sleep well, dream gently, and remember you are part of a universe that had a beginning that will have an end, but that in between contains more wonder than any single mind could ever hold. Good night.